Now that we've learned how to set up a equilibrium expression, we're going to go ahead and look at the mathematical involvement where we calculate equilibrium concentrations from the initial and the equilibrium concentrations. This is something we're going to be doing over and over for the next 4 chapters, and you're going to be so sick of this by the time you're done, the math will be automatic. We'll use a table that we're calling an equilibrium or a concentration table, but I call it an ice chart, and you'll see why in just a minute. So if we look at this equation, hydrogen gas plus iodine gas is in equilibrium to make 2Hi. I'm going to set up a little chart where I can write in numbers for my equilibrium and my beginning concentrations. So I'm going to rewrite this equation over here. Hydrogen plus iodine is in equilibrium with 2 hydrogen iodide. And on the left I'll write ICE, or ice. I is initial, C represents change, and E is the equilibrium concentrations. So if we look at this, our initial concentration and our equilibrium concentrations will always be in moles per liter, and as a result our change will be in moles per liter as well. So let's look at how we fill this in. We have 0.2 moles of hydrogen and 0.2 moles of iodine placed in a 2-liter flask. Now I'm not interested in moles, I'm interested in the molar concentration, so I'm going to have to figure out what the concentration is before I can fill this into my chart. At equilibrium, the concentration of each had dropped to 0.020 molars. What is the K sub C? Well, to start with, we need the molar concentration, so the first thing we'll do is calculate the initial concentration. I have 0.200 moles of hydrogen. That is placed in a 2.00 liter flask, so my molar concentration is 0.100 molar for hydrogen. Now I'll do the same thing for the iodine. 0.2 moles of iodine, and really it's just coincidental at this point that they are the same. Divided by 2 liters, that's not always the case, is 0.1 molar iodine gas. And you'll notice that these are both gases. This is not solid iodine. If it was, we wouldn't be including it. So now we'll go ahead and write out the mass action expression and plug in the numbers after we fill out our table. We know that K sub C is going to be equal to the hydrogen iodide concentration squared divided by the hydrogen concentration times the iodine concentration. So now we have to figure out how we're going to use our table to fill this in. We go back up here, and initially we've said that I have 0.1 molar hydrogen and I have 0.1 molar iodine. If you think about this, how much hydrogen iodide would I have to start? And the answer is 0, because before the reaction has started, we don't have any products. We just have 2 reactants. Now, at equilibrium, we were told the concentrations of each had dropped down to 0.020 molar. 0.020 molar and 0.020 molar. We need to figure out how much hydrogen iodide I have, and you do this sort of like a puzzle. How do I get from 0.1 down to 0.02? Well, I subtract 0.100 minus 0.020 is equal to 0.080. So my change is a negative 0.080, and that's how I get to 0.020 molar. I have the same thing going on over here in iodine. 0.100 is a starting, and it ends up at 0.020. So I get negative 0.080 molar, and now I'll end up with 0.020. Now this is the kind of tricky one. When I look at this, you see that I have 1 mole of hydrogen reacting with 1 mole of iodine to make 2 moles of hydrogen iodide. Since it's 1-to-1 stoichiometry here, I see that these are going down by the same amount. This is 1-to-2 stoichiometry. So the hydrogen iodide concentration has to go up by double that amount. So I get plus 0.160 molar. Now I want to point out that I'm not adding these two together. It's 1-to-1-to-2 stoichiometry. So one of these gives me 2 here. Because we could have some crazy thing where we had 2-to-3-to-7 stoichiometry or something like that, and you would multiply by whatever this coefficient is. So now if I take my 0 starting concentration, add in my 0.160 molar, at equilibrium I have 0.160 molar hydrogen iodide. So I'm going to get in the habit of using this equilibrium line to fill in my K sub C, or my equilibrium expression. So that's equal to my hydrogen iodide concentration, 0.160 molar, the quantity squared, divided by the hydrogen concentration, 0.020 molar, my concentration at equilibrium, times my iodine concentration at equilibrium, and that's equal to 0.0256 divided by 0.00040. Now I can only keep 2 significant figs, so my K sub C is equal to 64. So my equilibrium constant is 64. Now there's one for you to try on the next page. So go ahead and pause the video and try this problem doing the same thing to find the K sub C for this reaction. Okay, if you look at this, hopefully you got the same answer I did. My 0.20 moles of phosphorus pentachloride divided by 5.00 liters is equal to 0.040 molar PCl3, and my 0.10 moles of chlorine in a 5-liter flask, it's in that same flask, is equal to 0.020 molar chlorine. So now I go ahead and write my equilibrium expression. PCl3 plus chlorine is in equilibrium with PCl5. Setting up my ice chart, I have 0.040 molar, 0.020 molar, and 0. At equilibrium, I have 0.028 molar, 0.008 molar, and this is unknown. So now, how do I get from here to here? Well, I subtract minus 0.012. Oh, I'm sorry. We know that we have 0.012 molar over here. So 1-to-1-to-1 stoichiometry, I know that this has increased by 0.012, so each of these decreases by the same amount. That's a little bit different than the problem I did. Now we'll use the equilibrium line. I know K sub C is equal to my phosphorus pentachloride concentration